Hello, this is Bob Schmidt with another QC optimization video. This is one of a series of videos that's designed to provide a common language and understanding of quality control. The objective of this particular video is to help you understand power curves. This series of videos explores three concepts that are fundamental to quality control. They are stability, capability, and controllability. You're probably tired of hearing me say that, but I have to emphasize it. In the last video, we discussed capability, and you should now have a good understanding of that important concept. The next big topic is controllability. We'll cover that soon, but we need to take a short detour and talk about power curves before we can do that. Let's take another look at our system diagram that has the bird's eye view. We've already covered stability and capability, so you know what those are and what those contribute to quality control. As we saw in the last video, process variation is used to assess process capability. And you know that this is an important characteristic of a testing process. Capability is a performance index that's used to assess risk to patients. And we can only evaluate capability when the process is stable or in control. A process can be in two states, in control or out of control. We use capability analysis to determine risk when the process is in control. But how do we assess risk if the process is out of control? So remember from the last video, capability analysis tells us the size of errors we need to be able to detect when the process is out of control. And we call this the critical shift size. Our goal is to understand how to design a QC process that will detect a given critical shift size. We'll get there, but first we'll look at power curves. Statistical power is the ability to detect a change when one has occurred. In fact, a lot of statistics is concerned with detecting changes. This is a classic signal-to-noise problem. It's hard to detect a signal if there's lots of noise. Are you noticing a pattern? Noise is variation, and once again, variation is getting in our way. This time, variation is interfering with our ability to detect a process change. Consider this slide from the last video. Here we see a process shift has caused a significant proportion of our results to be unacceptable. This could impact patient care, and obviously, if this change occurred, it would be important to detect it as quickly as possible, preferably as soon as it occurred. This is the question we want to explore. Given a change in performance, or a shift, what is the chance that we'd be able to detect it? Let's go back to our process behavior chart, and let's assume we have a stable process. As you can see, there's no pattern in the data, so this is common cause variation. If we were to create a histogram by projecting all of the points on the graph to the left, it would look like a bell-shaped curve. The mean is 10 and the standard deviation is 1. The dark lines on the process behavior chart are placed at 1, 2, and 3 standard deviations from the mean. The lines that are 3 standard deviations from the mean are projected to the histogram. We see that very few values would exceed 3 standard deviations. In fact, if the process were stable, about 3 in 1,000 values would exceed 3 standard deviations. So that's pretty rare. And if it occurred, it would lead us to question whether a change had occurred. Let's imagine that we observe the red dot on the process behavior chart. It's greater than 3 standard deviations from the mean. What could explain this? Perhaps the process shifted to one side so that values that are greater than 3 standard deviations would now be more frequent. And this is indicated by the red arrow projecting back to the process behavior chart. This is a reasonable explanation because it would be very unlikely to see a result this extreme on the process behavior chart if the process were behaving normally. In other words, there must be an assignable cause. So let's set up a rule that says that a result greater than 3 standard deviations would be used as a signal that a shift may have occurred. In fact, this is a rule that's commonly used in quality control. We want this signal to work well because it's going to alert us to the fact that the process is out of control and possibly producing unacceptable results that could affect patient care. Given the signal, we will identify the assignable cause, remove it, thereby restore control and reduce risk to patients. Our question is, how well would this rule work, and what kinds of errors could the rule detect? So let's look at how this would work. This slide shows 3 different distributions. The distribution in the top panel is stable and has no shift at all. It's in control. The distributions in the middle and bottom panels are out of control and have shifted. The middle panel has a small shift, and the bottom panel has a large shift. The blue line represents the 3 sigma limit. Any result exceeding the 3 sigma limit would trigger our signal. In the top panel, we see there's a small probability that results would exceed the 3-signal limit, even though there has been no shift. The signal would go off and we'd waste time and money trying to find an assignable cause when there wasn't one to be found. The probability of this occurring is the probability of false rejection. This is an important property of any decision rule. For this rule, the probability of false rejection is about 0.015%, and that's pretty good because it's low. The middle and bottom slides show what happens when a real shift occurs. You can see the probability of detecting an error increases with the size of the shift. The bottom slide shows that the probability of error detection is 50% when the shift is 3 standard deviations. That's a pretty big shift, and we only have a 50% chance of detecting it. You can see that it would be better at detecting shifts of 4 or 5 standard deviations. Bottom line, this rule has a low false rejection rate, but it's not very good at detecting shifts. So we say that this rule is not very powerful. Recall that power is the ability to detect a change if one has occurred. Let's take the results from the previous slide, which is shown here on the left, and plot them on a graph. When the shift size is 0, there's a small probability that the signal will go off, and this is the probability of false rejection. We saw that the probability that a signal would go off increases with the size of the shift. The 3S rule has a 50% chance of detecting a change of 3 standard deviations. The rule would have a better chance of detecting bigger changes, and eventually the probability of detection would reach 100% when the shifts got big enough. This is a power curve. Given a detection rule, it shows you the probability of detecting a change. We would say that the power of this rule is 50% for a change of 3 standard deviations. So why should you care about this? Well, in the previous video, we showed how capability analysis could help us determine the critical shift value. This is the size of shift we would need to detect if we were not to exceed the maximum error rate. The power curve is important because it shows us the probability that we would detect that change. In the example here, we have a well-controlled process. We would only get into trouble if the shift size was 6 standard deviations. The power curve shows that we have a 90% chance of detecting such a shift. Thus, we would most likely detect it almost immediately, and there would be little risk to patients. So you should now understand how to read a power chart and also understand its role in quality control. As you can imagine, we can devise all kinds of rules to detect a process change, and every rule has a power curve. Power curves help us determine whether a rule can detect medically significant shifts in our testing process. This slide shows a series of power curves for 10 different QC plans. The plans are all based on the 3 standard deviation rule, but they involve repeated measurements of the control. The blue line shows the plan we evaluated previously, a single control at each level. The line furthest to the left shows the power curve for a plan based on an average of 10 controls. Here, we would put 10 controls at one level and plot the average of those results at each time point. Obviously, we can detect a smaller change if we have more repeats, but you can see there are diminishing returns. Going from 1 to 2 repeats provides a pretty big benefit. Going from 9 to 10 repeats has very little impact on power. This slide proves, yet again, that there's no free lunch. The curve on the left is the most powerful, but is also the most expensive. Selecting a quality control plan involves these kinds of trade-offs. You need to be able to interpret a power chart in order to select a QC plan. We can use a power chart 2 ways. Here, we can find the shift size that can be reliably detected by a QC plan. And by reliably, I mean that the error detection rate is 90%. You can see that the QC sampling plan with a single sample per batch can only detect big shifts of about 4.5 standard deviations. On the other hand, we can detect a shift of about 2.2 standard deviations if we use 4 repeats of a control in each batch and plot the average on the process behavior chart. Finally, we can detect a shift of about 1.3 standard deviations if we include 10 controls. This plan can detect small shifts, but it would cost a fortune. You can also go the other direction and ask, what is the probability for each sampling plan to detect a particular shift size? And here we see the probability of detecting a shift of 2 standard deviations. As you can see, you'd have less than a 10% chance of seeing a shift of that size if you used a single control. You'd have about a 50% chance of detecting the shift if you used a repeated control, and the probability of detection is about 100% if you were to average 10 controls. So once again, there's no free lunch. you need to spend more to increase the detection rate. This slide shows the impact of variation on power. And once again, power is the probability of detection when a shift has occurred. As the graph shows, variation decreases power. This is because variation increases the noise that hides the signal. Variation interferes with our ability to detect process changes that could have an effect on patient care. Perhaps you're detecting a theme. Once again, variation is causing harm. We've seen this over and over again in this series of videos. You're probably getting tired of me harping about this, but just in case you didn't get the memo, variation is bad. And variation hurts us in several ways. First, variation reduces the power of our control program, so we can't detect shifts. As we showed in this video, variation reduces our ability to detect process changes that could harm patients. Also, variation makes it harder to detect beneficial changes, so it's harder to improve the process. When variation is high, you only can detect changes that are large. Thus, you may miss smaller changes that affect patients or could improve the process. Second, variation decreases process capability. As you saw in the last video, capability is the ability of our process to meet requirements when the process is in control. That is, when it's stable. So you can see that variation is a double whammy. It makes things worse when the process is in control, and when it is out of control, it's harder to detect that the change has happened. Finally, as we showed in this video, variation increases costs. And there are several reasons for this. First, the lower probability of detection means there's an increased risk to patients, and this can be costly. Here I'm using cost in a generic sense to include the impact on diagnosis, prognosis, treatment, and outcomes. High variation leads to complex detection schemes that increase the false rejection rate. This too increases costs. And finally, based on the no free lunch principle, power is expensive. As we saw in this video, we can increase power by increasing the sampling, but this is expensive. The point is that variation impairs quality, and that's why process improvement focuses on variance reduction. QC supplies information on variation that can be used to drive improvement. Let's go back to our system diagram. We've now covered three components of the diagram. In the first video, we covered process control and common cause variation. As you can see in the diagram, common cause variation is an input to calculate the process capability, which is a measure that indicates the risk to patients when the process is in control. As you just saw, common cause variation is also used in power analysis to determine the size of error we can reliably detect. This can be compared with the size of a shift that we need to detect, which comes from the capability analysis. The final step is a back and forth process in which we compare various QC rules. We select a rule, determine its power, evaluate the cost, and compare the size of errors the rule can detect against the size of shifts that we need to detect to protect patients. Once again, quality control relies on three main concepts: stability, capability, and controllability. Let's quickly review what we covered in this video. We covered several important ideas. First, the idea of power. This tells us something about the performance of a QC plan. We need to know when the plan is out of control. Power is the ability to detect a change. We also saw that there's no free lunch. Probably already knew that. Power is expensive, and we can increase power by creating more complex detection rules or taking more samples. All of this costs money. And finally, we showed that variation decreases power. Given a control rule, increased variation decreases the ability to detect a change. In case you are not convinced, I reviewed many ways in which variation can harm patients and increase costs. Variation is the enemy in a quality improvement program. Okay, that wraps up this video, and I hope you found it useful. Please contact me if you have any questions or would like to talk about anything that was presented. Thanks for listening.